Very good morning. This is Dr. M. Shaktivel, Professor of AA and DS Department from Sri Shanmuga College of Engineering and Technology, Sangagiri, Salem. In this video, I'm going to discuss the topic bootstrapping from the course Machine Learning. So before start discussing about this topic bootstrapping, let me understand why do we need this bootstrapping, or when do we need bootstrapping. If you have small volume of data during our validation testing or insufficient data during our validation testing, to increase the volume of data, if you need a huge volume of data to predict the accuracy or to reduce the uncertainty of data, we need bootstrapping. So in real world, data and models are generally uncertain. We rarely know the true underlying distribution, and our data sets are usually limits or noisy. So bootstrapping helps us quantify and reduce that uncertainty without requiring strong mathematical equation. Let me discuss what is bootstrapping. This word bootstrapping came from the phrase to pull oneself by one's bootstraps. The phrase was used in 18th and 19th centuries to refer to an impossible task. For example, he left school at 15 and pulled himself by his bootstraps to ultimately head up a company. The phrase is believed to have come from the German author Rudolf Erich Rasp, who wrote about character who pulled himself out of swamp by pulling his own hair. Next, why bootstrapping is required? In statistical inference, generally relies on the sampling distribution and the standard error of the feature of interest. That in traditional approach or large sample approach draws one sample of size n from the population, and that sample is used to calculate the population estimates to then make inference. In reality, only one sample has been observed. So that what is this theory telling? Under certain conditions, such a large sample size, the sampling distribution will be approximately normal, and the standard deviation of the distribution will be equal to the standard error. But what happens if the sample size is not sufficient large enough, then it cannot necessarily be assumed to the theoretical sampling distribution is normal. This makes it difficult to determine the standard error of the estimate and harder to draw the reasonable conclusion from the data. When bootstrapping is required, if you have small size of samples, the population of or our data distribution is unknown, the statistics interest of is complex or non-standard. The next one is there is no analytical form or asymptotic theory to help estimate the distribution of the statistics of interest. The last one is if the distribution is not clean, then we need the bootstrapping. What is bootstrapping? Now let me try to understand the definition of bootstrapping given by the textbook author. So the bootstrap is a statistical procedure that resamples a single data set to create many simulated samples. This process allows for the calculation of standard errors, confidence intervals, and hypothesis testing. So this is this statement from the statistician Jim Frost. So this is the formal definition from the textbook author. Now let me see the informal definition or explanation of this. What is bootstrapping? So bootstrapping means something more specific and possible method of inferring results of results for a data from results found on a collection of smaller random samples of that data using replacement during the sampling process. So this relates back to the original phrase because it believes the sample is only relying on the smaller or itself to make calculation. In order to draw the conclusion or come to conclusion for the larger data or larger population. Next one is replacement and sampling. Imagine we have 5 different colors balls placed on a box. First we randomly pick a ball and replicate it to another box, and again move back to the original or the first box. Again randomly pick another ball and do the same thing what we did previously. We continue until as the first box contains 5 balls, then we are going to repeat this process for 5 times. So here the one question is, what is the probability of getting the all colors of balls? So when one sample with the replacement, the probability of selecting a particular color ball the same for each draw. Each draw is independent of others. So sampling with replacement is a method of selecting items from a data set in which each selection is replaced before the next one is made. The item can be selected more than once in the sampling process. So that is the replication may be or duplication may be possible. This is contrast to sampling without replacement, where each item can be selected by only once. 99.9% it is not possible. It may be if your data size is small, this may happen. So in large volume of data, suppose imagine more than 10,000 or 1 lakh data, it is not possible to get the exactly the what is the box A contains. We cannot replicate to the box B randomly. So this sampling with replacement is commonly used in Bootstrap resampling method. It's also used in Monte Carlo simulation and various other statistical computational techniques. How bootstrapping works? If you have sample of size n, it drawn from the population or any box or bag, let's call this sample as S. Let me call it this bag as S. Then rather than using a theory to determine all possible estimates, the sampling distribution is created by resampling observation with the replacement from S for m times, with each resampled set having n observations. Now if sampled approximately, S should be representative of the population. So therefore by resampling S for m times with the replacement, it would be as if m samples were drawn from the original population and the estimates derived would be representative of the theoretical distribution under the traditional approach. In this diagram, so from the left side we have main population, then this is this x1, we are drawing only some sample data from the main population. That is, we are taking x1, x2, x3 up to xn. This is our original actual sample. From this sample, now we are going to create resamples, or we are going to replicate, or we are going to copy of the not copy. So we are going to resample the data. So let me see the left side. We are resampling this x1 to xn. For our resampling 1 to represent, we have put in the star 1. In the next same way we are representing, we are resampling the another bag or another set of data from the actual data. So here x1 to xn we have represented, but for our understanding we have put 2 at the top of x. So it is not x power 2 or something. For our convenient only we have represented. So we are sampling up to m times. Suppose if you need 10 times, then we are the m value is 10, then we are going to resample 10 times. This theta 1, theta 2 is the estimate of the model parameters. Increasing the number of resamples m will not increase the amount of information in each set. So if our actual data size is 1000, then for if we are resampling for 10,000 times, every set or every bag contains the same amount of data, that 1000 only, that the size n will not vary. So n is the size of actual data, this m is the number of resampling. So this m, yes, You can vary any number of you want. If you 1 million or 1 billion, 1 trillion, whatever you want, you can resample. But every bag contains the size n. This will not change. This is the constant throughout for all or throughout for constant for all resampling. Let me discuss one example to understand the real-time applications or where we are going to apply or how to apply one real-time example for this bootstrapping. Suppose if someone wanted to know how many shoes he has, very simple. How to find out? He just suppose if how many shoes I have, then just I'm counting how many shoes, whether formal or informal shoes or something, or jogging or sports shoe. Yes, easily we can count how many shoes we have. But the question now, the question is how many shoes that everyone in his office owns. So now we want to know how many shoes owned by uh, everyone in our office. Imagine our company size is 1,000 people are working in the company. So asking each person how many shoes they have, it's impractical and time consuming. So now if we apply Bootstrap, how it works, how it calculate the average value or how it predict the value. Suppose if we are one day we survey out of 1,000, we survey only 50 people. 50 people, that 50 survey is the original data. Now we are going to replacement or we are going to resampling and records how many shoes each person has. So that actual 50, we are collecting survey from 50 people and we are recording how many shoes everyone is having. Yes, that original data or actual data is recorded. So now instead of repeating this procedure every day, we cannot again next 50% we cannot ask. So now what we are going to do, instead of collecting from the remaining people 50 per day, now we take that those 50 data points and create a lot of bootstrapped samples from that original or actual data. So each bootstrapped resample set has randomly 50 chosen samples with the replacement. For each of these samples, we measure the mean number of shoes owned. After doing so, there are 1,000 times. So we estimate, we 100 we estimate the average number of shoes for every our employees in the company is having average number. We are getting the average number of shoes owned by everyone. So he can. So now we can use we can calculate the confidence intervals and be able to conclude something like it's 95% likely that the average number of shoes owned by people in the company is between 4 to 6.